This video is part of a series in which we present the design of an 8-bit microcontroller core in System Verilog. In this video, we'll go over the instruction set architecture in outline. In other videos in the series, we'll go over the same material in greater detail. This is the program visible state of the processor core. There are 8 8-bit registers with the names shown here. 2 of the registers, X and Y, can be combined to form a 16-bit register called XY. Likewise, M1 and M2 are combined to form the 16-bit register M. There's also a program counter and a stack pointer. This is a Harvard architecture and not a von Neumann architecture, so the program memory and the data memory are separate. Presumably, the program is kept in a read-only flash memory, while the data is kept in a RAM. Both memories are up to 64 kilobytes in length, so addresses are 16 bits in size, so the program counter and the stack pointer are 16 bits in size. The address spaces for the program and the data are uniform with no special addresses. Execution starts at location 0 in the flash memory, and in the RAM, the stack will grow downward, so presumably it will be located in high memory. Not all memory need be present. There's also a condition code register that contains 4 bits. The condition code flags are the carry, the 0, the sign, and the overflow. And these will be set by the ALU instructions and queried by the conditional branch instructions. There are about 155 different instructions, which are either 1, 2, or 3 bytes in length. The first byte is always an 8-bit opcode. In the case of 2-byte instructions, the second byte is an immediate 8-bit value. In the case of 3-byte instructions, the second and third bytes form a 16-bit immediate binary value, and generally that is an address in either the program or the data memory. The instruction set can be divided into about 20 different categories shown here. Let's start with the move instruction. This moves a byte from one of the 8 registers into another register. This is a single byte instruction. There is no second or third byte. The registers are encoded in the opcode, so this actually consumes 64 different opcode values. Next, the move immediate instruction is a 2-byte instruction, so the second byte is an immediate 8-bit value which is moved into one of the registers. Next, we have the ALU group. There are 16 of these different instructions, and a 4-bit value in the opcode determines which instruction it is. This includes things like the logical operations, the arithmetic operations, and the shift operations. These will all set the condition codes, so we can do a conditional branch instruction after one of the ALU instructions. We also have a compare instruction, which compares the contents of the A and B registers and sets the condition codes. The load and store instructions move a byte from the data memory into a register or from a register into the data memory. These are 3-byte instructions. The second and third bytes form an immediate value, which is an absolute address into the data memory. We also have a load M and a store M instruction. These are 3-byte instructions, and the 16-bit immediate value is added to the contents of the M register to form the address, and a byte is moved from data memory into the A or accumulator register in the case of the load M instruction, and it's moved from the accumulator into memory in the case of the store M instruction. This instruction can be used a number of ways. If the immediate value is 0, then M is just containing a pointer, and we go to that address to fetch a byte. If M points to some structure in memory, the immediate might be an offset or the address of a particular field within that structure, and so we can use it in that way. And finally, the immediate value could be the address of a table or an array, in which case M is an index into that table or array. So in any case, we fetch a byte or we store a byte to main memory. The load code instruction goes to the flash memory, and it uses the XY as a pointer to determine which address we will fetch a byte from, and that's moved into the A register. Obviously there's no store into the flash memory, but there's also no ability to move a single byte from the memory providing a direct address. That's because we presumably know what bytes are in the flash memory, and if we want to grab a particular byte from the flash memory, instead of providing a 16-bit address, it makes more sense to just use a move immediate instruction and provide the actual byte itself. Next we have the add 16 instruction, which performs a 16-bit addition. It's a 3-byte instruction, and the immediate 16-bit value is added to something. And that can either come from the M register, or the XY register, or the A register, or it can be simply 0. In any case, the 16-bit value from M, XY, or A, which is 0 extended, is added to the immediate value, and that's moved into either the M or the XY register. So this instruction can be used a number of ways. If we use 0 here, we can use it just to load a 16-bit value into one of the 16-bit registers. If the two registers are the same, we might be using it to increment one of the 16-bit registers. We can also use it to transfer a value from one register to another register. We have 16 different conditional branch instructions, so there's a 4-bit condition field in the instruction which indicates which branch test to make. So the condition codes are checked, and if the condition is met and found to be true, then the jump will be taken. This is a 3-byte instruction, so the second and third bytes are an absolute address, and we take that jump. One of the conditions is always true, so this particular instruction is also used to encode the unconditional jump. We also have an indirect jump called go to XY. In that case, the target address is provided by the XY register. We have a number of instructions that use the stack. We have push, pop, call, and return. And we have a load SP instruction, which is followed by an absolute address, and that's just moved into the SP register. To push a register, we use this instruction, and we can push the value that's in any one of the 8-bit registers. Likewise, we can pop the top byte off of the stack into any one of the 8 registers. We have a call instruction, and that's given an 16-bit absolute address, and a return instruction to pop the address off the stack and return. All of our addresses are absolute 16-bit values. We don't use any PC relative addressing or any funky shorter versions of the address. They're all clean 16-bit addresses. I/O is handled with I/O registers, and there's a space of 256 possible I/O registers, so the immediate value in the in and the out instructions will address a particular register. The in instruction copies a value from a particular I/O register to the accumulator, and the out sends a byte from the accumulator to an I/O register. Finally, there's a no-op instruction. Now I want to talk about how the instructions are encoded. The move instruction moves a byte from one register to another. The source and the destination registers are encoded in 3-bit fields using the obvious encoding for the registers. There are several instructions that just use a single register, and these are encoded as shown here. These instructions are the load and store instructions, the push and pop instructions, and the move immediate instruction. There are a number of instructions for which we don't need to show which register is used. Any registers used are fixed and implicit. These instructions are encoded as we've shown here. As I said, there are 16 different ALU instructions, and they are all encoded like this. The 4-bit function code field indicates which instruction is intended. And we have instructions to do logical operations, arithmetic operations, and some shift operations, and so on. The operands always come from the A and B registers as shown here, and the result is always placed into the A register. All of these instructions will set all 4 of the condition codes so that after any one of these instructions we can use a conditional branch instruction. So we have 4 logical operations, AND, OR, exclusive OR, and the logical complement. And then we have an 8-bit addition instruction and an 8-bit subtraction instruction. In order to add multi-byte quantities, we also have an add with carry. We can subtract multi-byte quantities, and for that we have a subtract with borrow, or sometimes called subtract with carry. The carry flag is used to store the borrow from the previous byte's subtraction and will be 1 if and only if there was a borrow. We also have an operation to do negation on signed values and an instruction to clear the A register. We have 4 shift instructions. All shift instructions shift by 1 bit position, and all instructions shift the bit out into the carry flag, so the carry is set to whatever bit was shifted out. There are 2 left shift instructions. In the first one, a 0 is shifted in on the right side, and in the second one, the previous value of the carry flag is shifted in on the right-hand side. And likewise, there are 2 shift operations. The first one shifts a 0 in on the most significant end, and the second one shifts the previous value of the carry flag in on the most significant end. And finally, we have an increment instruction and a decrement instruction to simply adjust the A register. By the way, the forms shown here are exactly the forms that you would use in assembly code. So this is showing how these instructions are encoded in assembly language. Before looking at our example program, let's look at the conditional branch instruction, which is encoded like this. The opcode is followed by 2 additional bytes, which give the target instruction that we jump to if the condition is true. So there's a 4-bit condition code field, and that indicates which condition we are going to test for. The ALU instructions and the compare instruction will set the condition codes so we can do a conditional branch after one of those instructions. For example, if we compare A and B, we can then follow that with a conditional branch that will test, for example, whether they are equal, which simply tests the value of the 0 condition flag. What you see here in the middle column is exactly the way the condition would be specified in assembly code. These are slightly unusual lexical tokens, but that's exactly how you would write this particular condition test. So 8-bit values can be either considered to be signed or unsigned values. So we have 2 sets of comparisons for signed and unsigned values. And we can also test the condition flags directly. For example, we can test the sign flag with these 2 conditions, or the overflow flag with these. We can also test the 0 flag directly, or we can test the carry flag directly. We've also got a condition that is considered to be always true, and this is used for our unconditional branch instruction. And the 16th value is not defined. So next, let's see how the conditional branch instruction would actually be coded in an assembly language program. Here are the general forms of the conditional branch instruction and the unconditional variation. In this example, we see a compare instruction followed by a conditional branch instruction. We've specified the less than or equal unsigned condition variation here, and we are jumping to something called myLabel. In the second example, we are using an ALU instruction to decrement the A register, and we are testing whether it is 0 or not. In the final example, we see a simple unconditional jump instruction. Finally, here is the encoding for the add 16 instruction. Recall that the opcode is followed by 2 additional bytes, and those 2 bytes are added to a source, which can either be the XY register, the M register, or 0, or the A register, and the result is moved into the destination register, which is encoded with a single bit field. Well, that completes my description of the EveCore instruction set architecture. The next question, of course, is how are we going to build such a core in Verilog? That is the topic for other videos in this series, and I will see you there.